if you can press.
Yeah.
Okay, so welcome everybody. We are starting with this second webinar of the series on the NEANIAS space services that are services developed in the framework of the H2020 NEANIAS project. And today we are going to present the Latent Space Explorer, a service provided by the University of Milano Bicocca to perform unsupervised data pattern discovery on the cloud. And today, Professor Giuseppe Vizzeri and Thomas Cecconello are going to present it in more detail. So I stop my sharing.
And we start.
I think that, yes, Giuseppe and Thomas, you can start.
Okay. So, can you all see the screen?
Yes, we can see the screen.
Okay, thank you very much. We keep open the participants tab to look for latecomers. Thank you, Eva, for the introduction. We are going to discuss and present and demonstrate the working of a service that we called Latent Space Explorer, whose aim is to support forms of unsupervised data pattern discovery by means of a modern web-based tool that was designed and developed to be cloud ready. The work has been supported and completely developed under the umbrella of the NEANIAS project. And the motivation of the work came out during the initial phases of the project, in which we started interacting with colleagues from INAF and researchers in astrophysics. And we basically found out that there are a number of initiatives that are going to produce a large amount of data describing both phenomenologies that are already object of very active and already codified study, in which theories are already there and present and sometimes just need confirmations. But in some cases, the produced data call for the definition of innovative, novel, original classification schemes, because we're talking about discovery. We're talking about knowledge discovery, which is, of course, one of the most exciting enterprises in human research activity. The quantity, amount, and frequency of data produced by some of these novel observations simply overcomes our capacity to manually analyze this data. And moreover, it's really interesting to find out if computer science and artificial intelligence results in the area of machine learning in particular can actually support this kind of knowledge discovery. In a sense, a sub-area called data mining has been there for quite a long time. And of course, in a sense, the deep learning revolution has revitalized these kind of approaches. In fact, we see a lot of attention being paid to unsupervised or semi-supervised approaches in which deep neural networks are being somehow used without the need of large annotated datasets. So this is more or less the kind of scenario in which we are trying to set up this research and this new instrument. And of course, we want to couple these kind of under the hood considerations with something closer to the user, because of course we want to involve and want to have experts in the loop also, because we are talking about knowledge creation, and knowledge eventually has to be, discussed and manipulated by human experts from our perspective. And so we coupled this idea of having unsupervised approaches for machine learning coupled with visual analytics approaches, which is a bit more than simple data visualization, and in a kind of approach that has been already adopted to produce confirmatory results in astrophysics. We have a reference at the end of the slides, and which we'll provide. And this kind of workflow has also been applied in other areas. And this is really funny. For instance, for clustering artworks, which is, of course, probably one of the areas most far from science that we can think about. Okay, the tool we came up with essentially supports discovery of new knowledge by analyzing emerging patterns in the data itself. In a sense, throughout the process, you are pushed to explore the data set through the lenses of what we can call a latent space, and in a sense, we are going to talk about it shortly. And this process also has side effects, potentially useful side effects, like reflecting and finding out potential outliers, duplicates. Also, in case some kind of ground truth is present, one can also detect potential misclassification and detect issues in the preprocessing phases that somehow are made strikingly clear by looking at the disposition of the points associated to the pictures in a 2D or 3D space. And of course, this process needs to support an evaluation of the investigation process itself. So this tool also supports, in a way, exploring and comparing different representation learning models and approaches. In a nutshell, the proposed workflow is this one. We have a data set. Currently, the tool supports the exploration of data sets of images, and in particular, also, multispectral images specifically created in the context of astrophysics. But we also tested the workflow and the service with commonly used data sets of images from computer science. Of course, the first step is about data preparation, which is an important task, but we don't have time to talk about it now. And moreover, the service basically, considers that you do it outside of the service. The first step is to move from this cumbersome representation, that is the data set of images itself, to what we call latent space. That is essentially something that we achieve by applying representation learning techniques that essentially analyze the data set through models like autoencoders, variational autoencoders, generative approaches, and more recent approaches like contrastive learning. All of these approaches essentially try to employ and do effectively employ neural networks and deep neural networks without the need of a large annotated data set, essentially using the data as a teacher. What we achieve after this kind of process is the positioning of all the elements of the data set in a latent space that is a vector space that is much more manageable than the data set of images itself. But of course, it's still larger than what we can visualize in a 2D or 3D representation. So what we do next, we apply some dimensionality reduction techniques, and in particular, of course, the usual suspects like PCA, of course, but also more recent and more, effective in a sense, techniques like UMAP and TSNE. And by using this kind of dimensionality reduction techniques, we achieve a 2D or 3D representation. And directly on the latent space or on the reduced space, we can also finally apply clustering techniques. And therefore, we have an interplay between visual analysis of the achieved latent space. Of course, we have the possibility, in case labels are present, to visualize their distribution in this point cloud. But of course, we also want to finally perform clustering and show the user how the dataset can be automatically subdivided in groups according to approaches like the usual suspects, k-means, of course, density-based approaches, or other kind of approaches. What we're going to show you in a short while through a demo is the application of the service to a dataset that is not in the area of astrophysics, but is somehow relevant because it's a dataset of images taken from a satellite. Here I show you the RGB preview of some of these pictures and the different categories, so you can try to understand what kind of analysis we carry out. In this case, we pretend not to have the classification so that we can evaluate if the proposed workflow is producing some relevant results. And so if it's plausible to use in situations in which the ground truth is simply not there. Also, by means of this kind of approach, we can fine-tune the process and do some debugging of what we have in mind. What's also interesting is that here I show you the RGB preview, but actually the dataset is, in this case, Eurosat2 is very large. We don't just have the RGB channels, we have 13 channels, and so this is a multispectral images dataset. And so we have big data cube that is basically used to train, as we will see, autoencoders and another representation learning approach to get an idea of how this kind of process can work. And now, enough chit chat, we go for a demo. Thomas.
Hello, everybody. I'll show you the tool with the dataset that described a while ago, Giuseppe. Here you could see an interactive tool where the data are represented and plotted in a two-dimensional space by using a dimensionality reduction that in this case was pre-calculated, but in the tool you can calculate yours, which your parameters, your needs, you could choose the dimensions and you could send to the scheduler in order to be calculated. The points are a lot, and with high dimensions, are high dimensional, so it takes some time, and that's the why we are using a pre-computed reduction. Here, what I want to show to you is what an autoencoder learned, a simple autoencoder. And you could see the first site is that the classes, the colors you see are the labels, the ground truth labels, are not well separated. And furthermore, you could not draw lines to separate smaller groups, individual groups, and isolate to extract new knowledge. Now I show you the basic functionality, that is the exploration of the data by looking the position and what it is inside. That could help, but pass to another approach, another model, learned with contrastive learning, and you could see that the classes are much better separated, and some classes are spread into the spaces, like the purple one that represents the highway. That is totally reasonable if you think about it, because the highway is a structural building that pass through another land type, and so the features learned on those images takes into account the context of where the highway passes. So we see that there is some reasonable display of the data, and what you could do, let's say in a real use cases, we don't have the ground truth because we want to do knowledge discovery. So what we can do is to find natural grouping, or let's say clustering, into the latent space. So what you could do is perform clustering methods. As for the reduction, you could compute it with some algorithms that you could select from there and compute those in order to compare one with another, and to let you to help the users to understand what the clustering method learns. There are some tools. The first thing is to visualize the different the aspect of the points, to see why one point is in a cluster, why others are in another. For example, if you pick those small cluster that is wavy, that has a wavy pattern, it is separated from that one that is the same class, sea lake, but it's more, there are so much reflection, it's more noisy, and so on. This is from a first look, and maybe we could use different clustering method to have a finer, coarser grain of analysis. Let's say if I want to look at this specific cluster, maybe I want to I could choose a density-based method like DBScan to separate, to create more clusters and so on. On the right, you could see a panel where there are some metrics that could be useful to have a quality measure of your clustering, so you could choose which one is better. We have the silhouette that is explained by, for example, the cluster 6. You will see that is that one, the one on the left, is very well isolated. So you could see that the score is very high. Instead, for the red one, you could see that it's not very isolated, and so has a lower score. Other score, I don't want to go deep into those, are present, but could be useful. There is the distribution of the cardinality of each cluster. And there is a tool that could be useful if you have some non-ground truth, but some parameters that you pre-calculated or extract from a survey, from a catalog, photometric data, and so on. You could, for example, analyze the data, the cluster 6, and looks looks what there is inside that cluster and what characterize that cluster.
So in this case, we have the labels, but you have to think of categorical, for instance, characteristics associated to the points that the clustering approach has grouped together. So in this case, let's say, besides purely geometrical considerations that are those producing silhouette metric, here you could have instead, let's say, more semantical elements for evaluating the quality of the clustering. And for instance, if you look at the red one, for instance, if you look at cluster 2, okay, down on the word cloud, you can see that it's preponderantly you find the highway, but you also find other elements like industrial, permanent crop, pasture. In this case, it's ground truth, but in other situations, it would be I don't know, physical characteristics, physical features of images or of what is being represented by the image. So you have to think it as a way of evaluating / debugging your clustering, or a way of exploring the insights suggested by your clustering, and in case use these insights to propose new knowledge.
Passing now to real use cases, that is the analysis of supernova remnants images that are multi-band images. We have 200 pictures where you could see that there are some holes that was masked in the processing step because those are not object of interest, and we don't want the model learn those features. Here, we don't have known knowledge about the classification, and the motivation of that work is to find emerging grouping, emerging behavior in emerging pattern in the data, in order to help to classify or find new features useful to classify those type of sources. It's a work in progress. We have some preliminary results. And for example, here you can see in the 3D graphics some groups that are forming that seems to be related to the shape, to the structural shape of the radio, that is the red, the radio emission, that is the red one, and the position is even related to the remnants. So what there is in the background. Let's say the blue one you see there. So the relation of multiple features could help to find new groups and help domain expert to find to discover new classes.
Yeah, basically the example, one of the examples that motivated this approach was instead a confirmatory study in which researchers basically used a workflow that is essentially the same as the one we proposed, but they were basically analyzing, in this case, galaxies, and the study was confirmatory, meaning that there is a theory describing two classes of galaxies, and the study found out that by considering images, but also additional tabular data related to the galaxies, unsupervised machine learning techniques identified two patterns relatively well separated, which seems to say that the theory meets the data-driven analysis of the data. In other situations, we simply don't have the theory. We have a data-driven analysis that calls for an interpretation by the domain experts, also employing this kind of tool for comparing different ways to reduce the data, to produce latent spaces, and let's say they suggest different ways to interpret the data in what, from the perspective of researchers in the field of AI, is a peculiar approach, because there's been a lot of discussion on explainable AI. And in this case, we are not doing explainable AI. We are doing AI that calls and requires an interpretation and potentially an explanation by means of domain experts. For instance, in this case, domain expert could say that predominance of the red parts and the shape of the red part has a role in, let's say, clarifying that there are different types of supernova remnants related, for instance, to different types of supernovas. Of course, this is the point in which our competence ends and in which researchers from astrophysics need to fill in. And of course, consider that we had the first release of this service in, what was it, end of February?
Yes.
So we already have come up with ideas for changing, improving the service. For instance, it is perfectly clear to us now that the value of this visualization is lies not so much and not just in the possibility to, dynamically change perspective, explore it, but also compare it, because we have to understand if, for instance, this distribution of points is more or less informative for the task of, identifying groups than, for instance, the one produced by an autoencoder. And of course, there are limits. This data set is very big. We can decide to use different types of representation learning techniques. This data set is much smaller. It would be very hard to, train a SIM-CLR technique with this kind of data set. So we have basically succeeded in deploying this kind of service that can now be, employed to jointly study this kind of approach, in addition to studying data sets by domain experts. And we really hope that this kind of tool can be of use to other people in addition to the colleagues at ENAF that have already, considered this kind of tool. We can say something about how to achieve the point cloud starting from the image dataset, Thomas.
All the pipeline.
Yeah, let's say essentially here in this in one of these slides, like this one exactly, we have this step of representation learning. What you've seen in the demo is all on this part of the workflow and pipeline. But if you want to try and test this kind of system on your data, we can help you.
Yes, there is a GitHub repository. It's called the Latent Space Explorer generator that is useful to run some pre-configured models like autoencoder and contrastive learning methods to be used on different data set of images of FITS file and NumPy file and so on. There is a Docker image, so it's portable. It's easy to be deployed. And so I suggest you to start from there because the step there is the final step after the training, that is the inference step that set up the experiment folder as the tool requires. So but you could do even with your tools, with the PyTorch, with the TensorFlow, with whatever you want, by respecting the structure of the experiment folder and next upload to the cloud tool, the Latent Space Explorer.
So, few acknowledgements. What you have seen so far is working, is online. It's working under this URL. It's currently deployed in the GAR cloud. GAR is a very important and valuable partner of the project. So thanks to the GAR colleagues, some of which are also here. And of course, it wouldn't have been possible to do all of this work without them. And we are in the process of onboarding EOS with this service. We are looking forward to find additional application also outside the area of astrophysics. And this tool is also currently being used in the context of a hackathon. The hackathon registration is not possible anymore. This tool is not the central element of the challenges, but it has been proposed as a potential tool for analyzing, for instance, planetary data. And in fact, if I'm not mistaken, one of the groups of the hackathon is studying craters, and hopefully we can come up with some additional use case compared to those that we initially expected. But I guess this could be used also for different kind of pictorial data. And of course, we are glad that you found the time to participate in this webinar, and we are absolutely open to responding questions and curiosities. Here you can find some references to works I mentioned. The one about the application of this kind of pipeline and approach. Curiously, here it's called self-supervised machine learning, which is honestly, we have been discussing a lot with Thomas. This seems sometimes a new name for a well-known approach that is unsupervised machine learning with a different name. The paper has been available on the archive for some time, but has finally been published on the Astrophysical Journal. There are a couple of papers recently presented at the 20th International Conference of the Italian Association for Artificial Intelligence, one by us, one by colleagues that work in the context of the peculiar context of analyzing pictorial data related to arts, and of course a joint work presented at ADAS, at the ADAS 31 conference, to be hopefully soon published in the ASP conference series. There's been the first international conference on machine learning for astrophysics in Catania. That was a huge success. And also in that situation, some of the ongoing works have been discussed, and we hopefully will come up with a joint work discussing not just the technique, but also the domain level results. And of course, if you're interested, the prize award seminary of the hackathon will be soon announced, and hopefully we'll find out that the participants to the hackathon have come up with interesting results worth discussing and mentioning. So I think we can give space to questions, considerations, discussion. But we already thank you so much for being here and for your interest in this webinar.
Thank you very much, Giuseppe and Thomas. Of course, we are going to send an email with all the details and the useful links that you shared, so that people can try out the service and maybe give some feedback. If you have any question now, please feel free to ask.
Okay, Sebastian Luna Valero from AGI Foundation.
Hello, very nice presentation, thank you. So I think I went to one of the links, and so currently you need to log in to use the service, right? Or at least to see the demos, right?
Absolutely. Let's say that the process for, being able to use the system is twofold, if I'm correct. Thomas, please help us.
Yes. You have to log in. You need to have a Microsoft or a Google account, and you could log in like that, as I'm showing to you. And after that, you could see, you could access to the experiment list. We are removing a first step that is needed right now. That is by following the documentation, the access to the data sharing service, that is where you put your data. Okay, so in order to try the demo, we are fixing that part in order to let everyone to see the demo, and if they want, if you want to load your personal data, you could make that step.
But basically, as of this moment, let's say that prior to using this system, you need to have also logged in this, let's say, this additional service offered by NEANIAS and in the GAR cloud, that basically creates a space for you in the GAR cloud, a space that is, as of this moment, necessary to actually even see the examples. So if you cannot see the examples, it means that you have not yet created this space. This is going to change because, of course, for more immediate and less problematic and you know, quicker access to the demo and the pre-computed experiments, we want to remove this step. But you know, the first release had this kind of requirement.
Okay, great, thank you. So basically, it's only, I understand it's only enough and astrophysics, the domain that this service is being used for at the moment. You are aiming to expand the application to other domains and other kind of target groups, but at the moment that's the current audience, right?
Yes, absolutely. In a sense, the free examples with which we have, let's say, internally validated the approach are well-known data sets in the computer vision community. One is, let's say, like Machine Learning 101, it's NIST, that is basically the data set of handwritten digits. We have had some interesting results because, you know, handwritten digits can be of interest and can be also quite complicated. In some cases, for instance, we were able to detect that there are different ways to write 4. One closing the line, one with one just, you know, line and another with 2 different lines. And that can be somehow detected by means of this kind of approach. A much harder example to analyze is Celebar, which is a data set of headshots of celebrities. In this case, for instance, we found out that contextual elements influence the you know, the representation learning technique, and it's still not so easy to make sense of groupings within this kind of situation. And of course, Eurostat. In some of these situations, we realized that, as I said, data preparation phases are much more complicated than expected. In this case, we had reflexes on the water that generated lots of problems. And as you can expect, you never have enough, you know, computational power and time to perform experiments and compare. We are positive that the present tool makes sense for pictorial data. It can be used for tabular data, but probably it's overkill in a sense. We should find fairly complicated tabular data. It could be employed for anything that can be that can undergo a process of representation learning. In particular, it could also be used for embeddings of textual data, but the service should be seriously reconsidered, and that's something that is beyond the immediate, you know, future works.
Yes, or another type of data could be time series that are natural data that are hard to analyze because they are not semantically defined like the language and so on. But for example, for the pictorial data, we have the preview and it's clear how to show each point. For time series, we have to find a way to analyze this type of data in a useful way. So we have to contact different experts.
Yeah, in a sense, onboarding EOSC represents a good way of further understanding if this kind of work has a perceived value by different communities.
And that's my last question. What's the timeline to onboard into the EOSC portal, the service? Do you have any estimation?
Honestly, we are lacking a couple of documents that are not required but are soon going to be required about license and terms of use, which is of course important, but we were
in a month.
I think that in a couple of weeks it should be done.
Weeks.
Okay, good. Thank you.
Welcome.
Thank you for the question. Other questions?
Also, we are not just, of course, the work we have been doing so far with Supernova Remnants is probably a bit more advanced, but we are also working with other colleagues at INAF on other phenomenologies related to, if I'm not mistaken, related to the study, that the attempt to understand the dynamics of galaxy formation. Of course, the big problem is that we were lucky enough to find a way to develop and deploy this service that was not initially planned in the NEANIAS project proposal. But of course, again, thank you for finding the time to be here, because we are all overwhelmed with activities and things to do. So developing and proceeding with an interdisciplinary research that, by the way, lies exactly in one extremely interesting, exciting point, but also complicated one, such as knowledge discovery. Well, it's not simple, so it takes time. We are also in the process of working out a submission to a journal that is SoftwareX, that publishes essentially short papers describing open source project, and we are going to release this as an open source project. Also, in a sense, this is, let's say, this seems the right moment to do it, because also initiatives like TensorFlow has released in September 2021 a library called Similarity that represents an attempt to do something very similar to what we have been discussing. Of course, in a different way, with different techniques, but still in a very similar way. So I'm somewhat positive that there is value in this kind of approach, and of course it's about proving this with concrete results in domains of application, and producing services and tools that are really usable, which is surprisingly hard. As you probably all know, either working on the service development side or on the service user side. Whatever is your experience, I think you agree with me that finding proper tools to be used is very difficult. Okay. Again, we thank you very much for for being with us, for listening to the results we wanted to tell you about. And of course, if you don't have additional questions, I think we can close here and stop sharing. So we get back to seeing you. So thank you very much.
Maybe also you can stop recording.
Yes, we stopped the